Good morning and welcome back to Chapter 1. In this section, Section 5, we're going to be looking at the intermediate value theorem. A lot of the sections have a number of different topics. This one is very focused because the intermediate value theorem is something that sometimes trips people up. So we're going to focus on this. And so first thing is, what is the intermediate value theorem? And before I show it to you, the theorem does tend to I want to say it scares people because it doesn't make all that much sense when you first look at it, but it's actually almost a common sense type theorem, and we'll take a look at what it actually means once we read what it says. So it says intermediate value theorem, which can be abbreviated IVT because it's used that much. It says if f of x is continuous on a closed interval or a closed interval AB, and M is between f of A and f of B, then there exists a number C in that interval such that f of C equals M. So what this says is it's continuous, so there's no weird breaks or anything like that. So we know that the function is continuous. So as in the graph that just showed up here, there's no weird breaks. What it says is basically in order to go from f of A to f of B, since it's continuous, is it has to hit all of the values in between. It has to get everywhere. If it's continuous, in order to get from 5 to 7, it has to hit 6.2, somewhere in the middle. That's what the intermediate value theorem says. That's really all it says. It's going to hit it somewhere in the middle, which means that there's an x value that will have that y value. That's the f of c equals m part. So if we have numbers here, if f of a is 3 and f of b is 10, at some point it's going to hit 8.1. That c is the x value, which has a y value of 8.1. So that's all that says. A part that sometimes gets people is the m is between f of a and f of b. Why not just write it as f of a is less than m is less than f of b? Because f of b could be bigger. It could be f of b is less than m is less than f of a, and either one of these, it doesn't matter. M just has to be in between these two y values. A lot of times when we portray it, f of a is going to be smaller than f of b, and we have an increasing function. If we had a decreasing function, it would go backwards of that, but that doesn't make a difference. M is in between those two numbers. So we're going to see how we use this in just a minute, but before we do, let's look at some common symbols. I know that we've been using some of these symbols already, but now seems like a good time to make sure that we get them defined. So we have a few. The first one, we have this little E-like thing. It's like a little C with a line in it. It means it's an element of, or it's in the set of. So, example, C is an element of AB. That just means that C is going to be somewhere in between A and B. If it's not specified, it is assumed to be in the real numbers, but it just means that. So if we had C as an element of 1, 2, it means that C will be 1 point something, or 2.0, because it's a closed interval. It could be an open interval. That's not important. What's important is that little symbol there. This little, well, actually capital backwards E, just simply replaces the words there exists. It can replace a couple words around it. For instance, there exists a number, and then ST means such that. Again, it just replaces those words. And this upside down capital A means for every or for all. So a lot of times we'll have a theorem, and we haven't seen this one yet, but we'll get theorems that'll say for every m there exists a c in the interval ab such that blah blah blah, whatever it might be. So those come about a lot, and we use them because mathematicians don't like writing stuff down over and over and over again. We are what some people call lazy. Now, lazy is not a derogatory thing. It's just a very efficient way of saying efficient. So that's what lazy is. It's not that we lack the effort. We're just so efficient, we've shortened efficient. We have a symbol for everything. In fact, we have a symbol for everything. So if we wanted to look at what the intermediate value theorem looks like with some of these symbols, other than I've used the C already, we could rewrite the intermediate value theorem to look like that. Now it's a bit shorter. There's a couple things. So notice there exists a number is now just that. There exists a number C in the element such that f of C equals m. The only other thing that I actually took out here is on a closed interval, because the square brackets tells us it's a closed interval. Why is that in the intermediate value theorem? Just to specifically make sure that you're looking at a closed interval. It's repeating itself. And it does that purposefully. But technically, we don't need it. So this intermediate value theorem is exactly the same thing as the original. It's just written more efficiently. So how are we going to use the intermediate value theorem? Well, the nice thing is that it's always the same thing with very minor tweaks thrown in there from problem to problem. Specifically, we have 4 steps. The first step, you have to show that it's continuous on the interval. Now, it might give you an interval that it's continuous on. It might be continuous everywhere. If you're looking at a polynomial, that's always continuous, and you can just state it's always continuous. If you're looking at something with a denominator, it's continuous everywhere but whatever makes the denominator equal to 0. You just have to make sure that that number is not in the interval. So if we had something over x minus 3, it's continuous everywhere except for when x equals 3. So as long as our interval is 1, 2, it's continuous on that interval because 3 is not on that interval. So that's step 1, show it's continuous, which again is sometimes just stating that it's continuous because it's a polynomial, because it's an exponential, because it's something that we know is continuous. Step 2, find the y values at the endpoints of the interval. So we just have to plug them in so we can get the y values. Step 3, show that the value we're looking for is in between those endpoints. That is simply writing an inequality. The small endpoint is less than the value we're looking for, which is less than the big endpoint. If that is not the case, the intermediate value theorem doesn't hold, so you can't do anything. And then finally, step 4, make a very, very careful statement using the intermediate value theorem to make your conclusion. An example, and this is without context, we'll see some with context, but this example is what mine will always look like. Your statement does not have to be the same, but it does have to include all the different components of it. And so, like, this is the most concise, efficient, lazy way of getting everything into the same thing. And by using the same statement over and over and over again, I make sure I don't forget any of it. So the statement would be, since f of x is continuous on the interval, or if it's just continuous, it's just since f of x is continuous, and the m is in between the two values, By the intermediate value theorem, there exists a c in the interval such that f of c equals m. So let's look at a problem that uses this. Prove that f of x equals x to the fifth minus x squared minus 4 has at least one real root on the interval 0, 2. So, step 1, show that it's continuous. Well, it's a polynomial, so it's always continuous. I have it's continuous on r, on the real numbers. You don't even need that. You could just say it's continuous, and that implies on the real numbers. So that was showing it was continuous. Next, we're going to plug in the endpoints to find our y values. So f of 0, plug in 0, we get negative 4. F of 2, plug in 2, we get 24. We just need to show that there's at least one real root. If you forgot, a root is when it's going to equal 0. Well, what is 0 in between? It's in between a negative number and a positive number. A lot of times, we're going to be looking for 0. And so you just need to know that one of them is negative, one of them is positive. It doesn't even matter exactly what the number is, as long as you know whether it's negative or positive. So, we now, step 3, show that the value is in between those values. Negative 4 is less than 0 is less than 24. It's in between those two values. That's showing it. That's all that is. Then our careful statement. Since f of x is continuous, notice since it's continuous everywhere, I didn't have to put the interval. I could have, since it's continuous on 0, 2. And f of 0 is less than 0, which is less than f of 2. By the intermediate value theorem, there exists a c such that, there exists a c on the interval 0, 2 such that f of c equals 0. So we just proved that there is at least one real root on that interval. We don't know what it is. It doesn't matter what it is. We proved that it's there. That's actually a very important thing, because knowing that it's there before you start looking for it can be huge. And you can actually use this to approximate the roots. That's actually what your calculators do when you use them to find a root. It's from 0 to 2. Okay, so there's a root there because one of them's negative, one of them's positive. So then it'll cut it in half. It'll plug in 1. Turns out 1 is also negative. So now we know there's a root between 1 and 2. And then it'll plug in 1.5. It's either negative or positive, and so it'll narrow that window down by half. And it'll do that a whole bunch of times very, very quickly to get a really close approximation to the root. That's called the bisecting method of approximating a root, if it ever comes up. So, here we use the intermediate value theorem to show that it has at least one real root on the interval. We're going to do another one. In this case, prove that root x minus 5 equals 1 over x plus 3 has at least one real root. Here it did not give us an interval, so we're going to have to pick an interval to use. That will be some trial and error. Practice makes your trial a little bit more efficient, but it could still very possibly be some trial and error. But the process is going to be the same. So the first thing I'd actually do is we don't want stuff on both sides of the equal sign. So let's subtract, make it a function. F of x equals the square root of x minus 5 minus 1 over x plus 3. Well, when is it continuous? It's continuous when x is greater than or equal to 5, because that's going to be a domain for underneath the root. We can't have a number less than that because we have the square root of a negative. It's not going to work. So we know that it has to be greater than or equal to 5, and x can't equal negative 3, because that would make that 0 in the denominator. Now, negative 3 is not bigger than 5, so this one doesn't really make much of a difference in our case. But if, let's say, this was x minus 7 in the denominator, x couldn't equal 7, so we would just have to make sure not to include 7 in the interval. So, as long as we are above 5, it'll be continuous. So now we need to pick some values. What value to pick first? I would pick 5. That's where the domain starts. So a lot of times things will happen in that area. Also, plugging 5 into the square root of x minus 5, it's a number that I'm going to be able to do in my head. I like that. So let's plug in 5. We get square root of 5 minus 5 is 0, so that's 0, minus 1 over 5 plus 3, that's negative 1/8. Now we need to plug in another number. We can't go less than 5 because our domain has to be greater than or equal to 5. And so let's go bigger. I would choose the next biggest number where that square root is going to be pleasant. That next biggest number happens to be 6. Because 6 minus 5 is 1, we can do the square root of 1. Is that always going to get us what we want? No. We might get another negative number there. In that case, move to another number. Move to a bigger number. Move to a number closer to 5. Again, trial and error can take place in this kind of thing. In our case, we plug in 6. We get square root of 6 minus 5, that's square root of 1, which is 1 minus 1/9. That is going to be a positive number, 8/9 specifically. So we have a negative, we have a positive. We know that 0 is going to have to be in between them. And then we can make our statement. Since f of x is continuous on 5, 6, it's the interval that we used, and f of 5 is less than 0 is less than f of 6. By the intermediate value theorem, there exists a c in the interval 5, 6 such that f of c equals 0. Notice the structure of that sentence was identical to my last one. It hits everything. Things you need to hit: you need to make sure you state that it's continuous. You need that the number is in between the other two numbers. So we have continuous. You do have to reference the intermediate value theorem. That is actually important. And if I am going to forget something in this sentence, it's by the IVT. I assume it's the IVT, but that is something that you do have to put. There exists a c in the interval such that f of c equals 0. So basically everything that the entire sentence is what we need. There's no superfluous stuff. I know I say the entire sentence and you look at this and you think that's a sentence. Yes, it is. It is a perfectly valid, grammatically correct English sentence. And so, using the intermediate value theorem, we saw two examples. They're both basically the same. This is what we do. We don't have to be looking for 0. We could have it equals 3 at least once. We'd be looking for things where one of them's bigger than 3, one of them's less than 3. We could subtract 3, so we'd have blah 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 minus 3 equals 0. But it's the same. We're just looking for the existence of that number. And so that's what the intermediate value theorem says. Now, what's also important is what's it not say, because this can get people in trouble sometimes, because they like to say, oh, the intermediate value theorem says this, and then no, it doesn't. One thing it doesn't say is where that c is. We know that it will exist somewhere in between those two numbers, but we don't know where it is. Even if it's like, it could be halfway, it could be right next to it, we don't know. It's just in between there. How many times the function equals the y value? We could have f of a, there we go, f of a, f of b, and the y value. We could, and then, well, I won't put a and b, but we could have a line going straight up. Hey, it equals it exactly one time. We could have a line that goes like that, or it equals it a whole bunch of times. So we don't know how many times the function equals the y value. We know it equals it at least one time though, because in order to get from this number to this number, it has to at some point hit every number in between. Again, it could hit it more than once, it could hit it less than once, well, not less than once, it could hit it more than once, it could hit it exactly once, but it will hit it at least once. Anything about y values outside of f of a and f of b? So if we have a graph with f of a, f of b, let's say our m is up here, it's not in between there. The intermediate value theorem doesn't tell us anything about that. A lot of times people say, oh, well, it can't equal that. That's not true, because we could have a function that goes like that, where it equals it, and then there's my a, here's my b, and so in between here and here, it goes from f of a to f of b. It goes bigger than that, which it can. It doesn't have to. These guys up here, it didn't go outside of that range, but it could. We don't know. The intermediate value theorem does not tell us anything about that. So you can only say stuff. If it goes from a to b and it's continuous, or f of a to f of b and it's continuous, it has to hit everything in between there. It can or it cannot hit stuff outside of there as well. And finally, it does not say anything if it's not continuous on the interval. If there's a great big break in the graph, it could do anything. Like we can't say anything. So that continuity piece is hugely important. So that's what the intermediate value theorem does not say, which is important to know, but also knowing what it does say, being able to use it, that's important. So this is what you're working on today. There's not all that many problems, but they actually do take a few steps. And yes, you do have to write out those few steps. So take the time on the few problems that you have, and then make sure you're working on problems, make sure you're asking questions, and happy mathing.